Hello, Professor. We are a group of five. My name is Amanda. Soren is unable to make it, but he did work and help us out with the code. Shirley, Lou, Zachary Milano, and Rachel Ryan are also in this group. We aim to predict the significance of earthquakes, and we found the data off of Corgus. And so here's the data below. We had to import a lot of stuff in order to get some of our models, especially the animation, to work. So here's just a little snapshot of the data that we downloaded. It is 8,394 rows long, and then it includes like separate earthquake information. But we just wanted to focus on the location of the earthquakes, the magnitude of the earthquakes, and the depth of the earthquakes to try and predict the significance of it. So here we're just naming it and printing it each data off to make sure we had it right. And then we create objects for each column description of individual earthquakes that we thought would be the most important in determining the significance of the earthquake, subsetting the data. This also made it easier for us to reference the data later in the project. So we first did a fitted model for significance or for magnitude on significance of the earthquake. And we found that the model explained 83.5% of the variance in the significance variable in our data. So magnitude is a fairly good predictor of earthquake significance. This model would not predict the significance of earthquake with very small magnitudes very well, since the intercept is negative. A negative significance does not make contextual sense. If we pursued this research further, we might consider focusing the intercept to be 0 in order to predict the significance of earthquakes with small magnitudes, but that has some drawbacks.
So after we fitted that model, we decided to try another one to see if we found something to be better. So we tried model 2, which is regressing location on significance, so the location variable, and this was the result of what we got. There are a lot of different intercepts, one for each location, so it's kind of a complicated model. And the reason we thought that location might be a good predictor of significance is because basically tectonic plate movement has a lot to do with earthquake activity. So locations that are near tectonic plates that are very active might be more likely to have significant earthquakes, or vice versa. Those that are not in very active locations are probably likely to not have very significant earthquakes. In addition, we thought that some locations or countries are more developed, so their architectural codes for building might be a bit more rigorous. So an earthquake would affect their area less, like the buildings would withstand it, whereas some areas' significance of an earthquake could be really intense because a lot of their buildings collapse. So our model turned out to be actually pretty good. It accounts for about 77.3% of the variability in significance. But again, a drawback to this model compared to the other one is that there are a lot of different intercepts, so it's kind of complicated graphically as well as just when you're looking at it in general. So perhaps the other model is better.
Right here, we have a model where we're plotting location and magnitude on significance. So when we add both of these into the model to predict for significance, we get a higher adjusted R squared. You can see right over here, compared to our other models. We took this into account. We took into account the additional complexity of having two variables. So we know that both location and magnitude are more significant predictors together than they are apart. We also wanted to test how correlated they are to give a little perspective when reading the results. In the correlation model, we found that they were highly correlated. This makes sense because the placement of tectonic plates is very related to how large an earthquake will be produced. This explains why alone location and magnitude explains a large amount of variation in the earthquake significance. So depending on how we want to use this regression, we might value the simplicity of the model just taking the variable of magnitude into account for earthquake significance.
We thought the depth of the earthquake might affect the significance because the movement of tectonic plates might be more destructive if the plates are actually closer to the surface. So we added it to our existing best model, which is model 3. Unfortunately, we noticed that the adjusted R squared actually decreased, which means that the additional variable that we added did not explain enough additional variance in the significance variable to compensate for the complexity it added to the model. So looking at our model, depth of the earthquake might actually affect the significance because the movement of tectonic plates might actually be more destructive if the plates were closer to the surface. So we added it to our existing best model, which is model 3. Unfortunately, we noticed that the adjusted R squared actually decreased, which means that the additional variable we added did not explain enough additional variance in the significance variable to compensate for the complexity it added to the model. So looking at our 4 models, we decided that model 3 was the best predictor for earthquake significance. In this line here, we were interested in linear regression plot for 2 numeric variables by using red plot. So we decided to use an interactive plot, and this graph actually shows the regression of magnitude on significance as well as all the other data points. We see that the data is actually somewhat curved, so our data would likely fit better with a polynomial model. Towards the high magnitude data points, our graph underestimates the significance. This might also be explained by the fact that high magnitude earthquakes are less common. So the graph is attempting to fit the data well that is mostly from the lower magnitudes. This is something we should definitely keep in mind when sharing our model with other people. Overall, we were able to see the weakness and successes of our model by plotting it. If the animation had actually worked, we would see how the model adjusted to fit our data point. The animation had actually previously worked before, but we're just having some trouble now. But a future project could possibly include a polynomial term in the animation.
This graph right here to be animated. We spent 3 or 4 hours in addition to the time that we spent on the rest of the project trying to get this graph to be animated. We couldn't manage to do it. We had it working at one point, and then somehow it stopped working. We spent a lot of time trying to get it to work, and we've decided to accept defeat on the animation portion of this graph. I don't know, do you guys have anything to add?
Thanks for
I-
listening.
yeah.
Yeah,
Thanks
thank
for
you.
listening.